Good morning, guys. Good morning. Good morning. Good morning. Today we'll be doing our first learning unit for the day, which is describing the principles of computer programming. But first, I would like to inform you that the videos will be uploaded on the e-portal. So each and every day, precisely, so each and every after 2 days or 3 days, there will be videos uploaded on the portal. We'll do each unit standard, and after doing a unit standard, there will be activities uploaded on the portal. So we'd like you to engage more and answer those activities so that we could see that you are participating. So let's get to the business of the day, which is describing the principles of computer programming. I am Kabelo Mashilo, by the way. I'll be your facilitator throughout this System Development NQF Level 4. So the purpose of this unit standard, um, it's to provide a conceptual knowledge of the areas covered for those entering the workplace in the area of system development, as additional knowledge for those wanting to understand the areas covered. And people accredited with this unit standard are able to describe problem analysis and program design techniques, describe different data representations used in computer programs, and describe basic programming principles. Described the principles used in designing a computer program, and this performance of all elements is to a standard that allows for further learning in this area. So let's get into our session of the day, describing problem analysis. Let's start there. What is describing the problem analysis? I've done a slide on this, which uh, which is problem analysis in computer programming is the process where we break down problems into components so that the problems can be easily understood. So we need to identify the problem, and then we need to break down the problems into components so that those components are easily understandable to us. So after the analysis of the program that is being broken down, so now after the analysis, understanding the problem, figuring out after you've figured out the problem, what is it? Now the problem, now the program, it is possible to list out the steps that must be followed for the solution. Those steps are the ones that are mentioned on our learner guide. So we've got 7 steps, 7 steps processes program development. So we need to understand the problem. We need to understand the problem, plan the logic of the program. We need to plan. So after we have understood what is the problem, you need to plan the logic of the program. You need to code the program using a structured high level computer language. So I just want to touch base on the high level computer language, what that is. It's your programming languages, which I'll mention just a few. It's your Python, it's your Visual Basic, Delphi, Perl, PHP, ECMA script, Ruby, C Sharp, and Java, just to mention a few. Those are our high-level computer languages. So now, after 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 using a structured level computer problem, we need to use a compiler. Using a compiler, what can you think of when they say using a compiler to translate the problem into a machine, a language? A compiler, it could be a programmer, a programmer. You could be a programmer after completing this NQF levels 4. You can further your studies, end up being a compiler, a programmer. to translate these programs. You can compile for C Sharp, or for Java, or for Python for that matter. So after compiling that, you need to test and debug the program that you have compiled. You need to test the program before you are sure whether this program is it ready to be uploaded on our computer. You need to test and debug the program. But the problem put the program put the program into production, which simply means you need to put after testing, you need to put the program into production to check whether this program is it fine, is it fine now for use now, and then maintain and enhance the program. That simply means you need to maintain the program. In a program there are fixes and there are bugs. So each and every time you need to, as a compiler, you need to check whether your program needs to be fixed there and there, and the user needs to download those kind of fixes to have your program in a high level, as safe safe for the environment or for users, if I may put it that way. So planning the logic of the program requires the development of algorithms. An algorithm, I've I've explained it here further to say, an algorithm, as defined, is a sequence of instructions designed in such a way that if instructions are executed in specific sequences, the desired result will be obtained. So one thing that I haven't mentioned, the details of the steps that are mentioned on there are written for the computer in order to produce the desired result. So these sets of these steps is commonly known as an algorithm. So an algorithm is a sequence of instructions. A sequence of instruction. What do you understand about an algorithm? Is a sequence of instruction. I'll make an example. Let's say I'm having a car, and I'm approaching a stop sign. So what is the first thing to do? The stop sign tells us the car has to stop. There's an instruction, and then when there is no car, I'm safe to proceed to move the car. So when you reach a robot, so when the robot is red, what does that tell you? The instruction tells you the car has to stop. When the robot turns into a green, when turns to green, that instruction simply states tells you that the car has to go. So those are the sequence of instructions. So an algorithm is a sequence of instruction which is designed such that those instructions are executed. Those instructions are executed in a specific instruction, and the desired result will be obtained, which simply means the outcome of that is for the car. For example, if the car approaches the stop sign, the outcome of that, you want to see the car stopping. The instruction is for the car to stop and the car to move when it's safe to do so. So as I've explained, an algorithm, what is it? Let me further read from your learner guide which means that a human readable representation such as the flowchart and the pseudocode are typically used to describe the steps of an algorithm and the relationships among the steps. So a flowchart is a graphical representation of the steps and control structures used in an algorithm. So these are the flowchart are graphical representation of the steps and control structures used in an algorithm. A flowchart does not involve a particular programming language, but rather uses a set of geometric symbols. Let me explain that. So let's say we approach a stop sign. So using a graphical representation in a set of geometric symbols. So geometric symbols will be your plus sign, your equal sign, your multiplication sign, your minus sign. So let's say, for instance, a car, when its instruction is to stop at the stop sign, we will use a geometric symbols, which is a plus sign, additional sign, which is a plus plus. So when we see a plus plus, we know that is a stop sign when we reach a stop sign. So when we use a geometric symbol, a minus sign, that simply means it is safe for the car to move because there is no car. So that is a graphical representation, but that it does not involve a particular programming language. It's just a set of geometric symbols and the flow control line to describe the algorithm. It further describes the algorithm, which is a set of sequences. So we use those geometric symbols just to describe the algorithm much more better. So from a flowchart, a program. So these things are just a flowchart. So from a programmer in a point of view, he will just use these uh, a set of geometric symbols to justify or describe further the algorithm, the sequences, the instructions, set of instructions in a sequences manner. So now a programmer can produce the high level code required to compile an executable program. The introduction of of structured programming, which was in the 1960s and 90s, 60s and 70s, I beg your pardon, 60s and 70s, brought with it the concept of structured flowcharts. So the structured programming paradigm evolved from the mathematical proven concept that all problems can be solved using a three types of control structures, which is sequence, decisions or selective or selection or iterative or looping. The definition of structured flowcharts used in this document and software further defines the three types of sequential structures, which is process, input, output, and subroutine call. And the other ones are three types of decision structures, which is single branch, double branch, and case. And the four types of iterative structures: test at the top, test at the bottom, counting, and user control exit. A comment structure. The SFC program is designed to aid the programmer in designing and representing structured flowcharts. So we'll identify the problem analysis technique, which is the top down and the bottom down, which are both strategies of information processing and knowledge ordering used in a variety of fields including software, humanistic and scientific theories, and management and organization. A top-down approach, also known as stepwise design or deductive reasoning, and in many cases used as a synonym of analysis of decomposition, is essentially the breaking down of a system to gain insight into its compositional subsystems. An overview of the system is formulated, specifying but not detailing any first level subsystem. Each subsystem is then refined in yet greater detail, sometimes in many additional subsystem levels, until the entire specification is reduced to base elements. Let's move down to our bottom up, which is one of the techniques. Bear in mind, it's one of the techniques. A bottom-up approach, also known as an inductive reasoning, and in many cases used as a synonym of synthesis, is the piecing together of systems to give rise to grander systems, thus making the original system subsystem of the emergent system. Bottom-up processing is a type of information processing based on incoming data from the environment to form a perception. And in a bottom approach, the individual base elements of the system are first specified in great detail. These elements are then linked together to form a larger system. Guys, I just wanna to explain this to say I will highlight on your learner guide. I will highlight the most important part. You are required also to read through everything to understand better. So whenever there's something that you don't understand, please feel free to engage me on the platform that are given, your WhatsApp group, more importantly, your portal. We need to engage. We need to see that we are participating in this sort of engagement. So now let's go down to our product design and development. During the design and development of new products, designers and engineers rely on both a bottom-up and top-down approach. We need to remember our bottom-up, our bottom-up, our bottom-up and down. Our bottom-up are problem analysis techniques, which are two. A problem analysis technique. So the product design in development, the product design and development mm, of new during the design and development of new products, designers and engineers rely on both a bottom up and down approach. So the bottom up approach is being utilized when when off the shelf or existing components are selected and integrated into the product. An example would include selecting a particular fastener such as a bolt and designing the receiving component such that the fastener will fit properly. In a top-down approach, a customer fastener would be designed such that it will fit properly in the receiving component. Let's go down to our next topic, which is modularity. Modularity is designing a system that is divided into a set of functional units named modules that can be composed into a larger application. A module represents a set of related concerns. It can include a collection of related components such as features, views, or business logic, and pieces of infrastructure such as services for logging or authenticating. I just want to repeat that. A module represents a set of related concepts. It can include a collection of related components such as features. Those features could be views or business logic, and pieces of infrastructure such as services for logging or authenticating users. Those services for logging, for example, let me give you an example of that. For instance, now you've got an e-portal. You need to log on. You need to log on onto that system and authenticating. You need to put on your credentials, your password. That is authenticating users. So now a composite application exhibit modularity. For example, consider an online banking program. The user can access a variety of functions such as transferring money between accounts, paying bills, and updating personal information from a single user interface. These modules communicate with each other with back-end systems such as database servers, application services, integrate components within the different modules and handle the communication with the user. So I just want to repeat that more precisely of the example that was given to say a composite application exhibits modularity. For example, consider an online banking program. Thus, the user can access a variety of functions such as transferring money between accounts, paying bills, and updating personal information from a single user interface. So when you for instance, for example, let's say the e-portal that you are given, it's in a form of an online banking program. That's for you. When you authenticate, you are in a form of a single user interface. You need to transfer a certain activity to your friend. So now we need to process those kind of things. So those are just an example that I'm trying to give you just to understand in terms of what do they mean in terms of that. So these modules communicate with each other and with a back-end system such as a database server. Database server is where all your credentials are there on the server. So the application services integrate components within the different modules and handle the communication with the user. The user sees an integrated view that looks like a single application, but at the back of the system, there are many things that are happening within the database server. There's an application services integrated component within the different modules and to handle the communication with the user. So there's a lot that is happening around. So that is what they're trying to explain. So for instance, now there's an illustration on this there's an illustration which explains more of a composite application which has a shell and hosts all the visual components, and application services provide the glue between the modules and the shell, contain the vertical slices of the application which has the module under the application which has the view and the services. So what will be the question to say, why would I want to choose a modular design? Why would I want to choose a modular design? Design. So this is the following scenarios to describe why you want to choose a modular design for your application. So properly defined simplified modules, properly defined modules have a high internal cohesion and loose coupling between modules. The coupling between the modules should be through well-defined interfaces. Developing and deploying modules independently. Modules can be tested, or deployed on independent schedules when modules are developed. So modules can be developed, tested, or deployed. Modules can be developed. So modules can be developed, tested. So you can test a module and deployed on independent schedules when modules are deployed in a loosely coupled way. By doing this, you can do the following. You can independently version modules, you can develop and test modules in isolation, you can have modules developed by different teams. So for I could give a brief example about that. So let's say maybe we have a program. You have developed a program for students to access videos there. So now you wanna deploy this and test this system, this program, that it is working. So we've got a schedule for it to say on Saturdays the students won't be accessing the site. So you wanna deploy it at that time. You wanna test that program at that time. So those are the kind of things that we mean in terms of test and deploy on independent schedule when the modules are developed in a loosely coupled way. So now let's move into loading modules from different locations. A Windows presentation foundation. Let's go back. Let's go to our slide. I've explained further what is Windows Presentation Foundation, which is a free and open source graphical subsystem. So a free and open source, it simply means a programmer, a compiler can manage, can open a program and fix the program to his standards. So a free and open a source graphical system originally developed by Microsoft for rendering users interfaces in Windows-based application. So the WPF application might retrieve modules from the web. So this was deployed by Microsoft. So it retrieves modules from a certain web. There's a certain site that it goes. there. So Microsoft developed this application, so that a compiler can retrieve modules from the web. So a compiler can retrieve modules from, because now it's a free and a source a graphical subsystem originally developed by Microsoft. So a compiler can go to the web and retrieve these files from a file system, or from a database. A silver light application might load modules from different sharp files. What is a sharp file? A sharp file is a file format used to distribute and install application software and middleware onto Microsoft Windows operating system, and is the file format for silver application. So we need to bear in mind that the WPF, which is the Windows Presentation Foundation, provide developers, compilers, programmers with a unified programming module for building line of business desktop application on Windows. So now this, it goes to the web, where a compiler will want to retrieve a module file. Once retrieving that module file, now that that module file, he retrieves it for building inline businesses desktop application on Windows operating system. So let's go back to our slide, where we were. However, most of the time the modules come from one location. For example, there's a specific folder that contains the modules, or they are in the same file, in the same sharp file that I've explained, to say the modules come from a one location file. So you could go to a web where that web contains the modules in a singular file. So you go straight to the specific sharp file where you will find these files. So minimizing download time. When the application is not on the user local computer, you want to minimize the time required to download the modules. So if that application is not on the user local computer, a compiler would want to minimize the time required to download the modules. To minimize the download time, only download modules that are required to start up the application. To minimize the download time, only download modules that are required to start up the application. The rest are loaded and initialized in the background when they are required. Minimize application startup time. To get part of the application running as fast as possible, only load initialize the modules that are required to start up the application. To get part of the application running as fast as possible, only load initialize the modules that are required to start up the application. Loading modules based on rules. This allows you to load modules that are applicable for a specific role. An application might retrieve from a service the list of modules to load. So now we need to describe the programming design techniques. So what's a pseudocode? A pseudocode, I've explained it on our slide, is an informal high-level description of a computer program or an algorithm. So it's a high-level description of a computer program or an algorithm. Bear in mind, an algorithm, it's a sequence of instruction. So now this is a high level description of level of level of sequences. It's a high level description of a computer program or level of sequences. It is written in symbolic code, which must be translated into a programming language before it can be executed. So I've got an example here of the pseudocode. It's if else statement. It's your instruction telling that solve for quadratic equation for math. This it's for math. It's an example for math. So now, as we could see on the on the on the example, it simply tells that if else the example on the code. It simply tells that if else as the example on the code. There's nothing that it says much. It's just an example and gives you an understanding of pseudocode, what it is all about. So let's go back to our learner guide. Our learner guide, our learner guide, our learner guide, our learner guide. So a pseudocode and a flowchart are both popular ways of representing algorithms. A pseudocode has been chosen as the primary method of representing an algorithm because it is easy to read and write and allows the programmer, the compiler, to concentrate on the logic of the problem. Pseudocode is really structured English. It is English that has been formalized and abbreviated to look like the high level computer languages. Their approach is to write the program in a language similar to the one used for implementation, but when with an easily understood shorthand for complex expression. Hence why from our previous example, it's just a statement to say, hey, you're approaching a stop sign, stop. So it's just a structured English. It is English that is formalized and abbreviated to look like the high level computer language. So the idea, the approach is to write the program in a language similar to the one used for implementation, but with an easily understood shortened for complex expression. The idea is to represent the logic but to ignore many of the syntactic requirements of the programming languages. A pseudocode design description is thus a mixture of human language and programming constructs. Instead of complete logic of well-known functions, simple statements are used. Similarly, the program flow can represent with traditional conditional statements using written expression to describe the logic. While there are no generally accepted pseudocode notation standards, it is a good idea to use language constructs that are similar to those in the high-level language being used. When you do, the pseudocode will look familiar at implementation time and will provide a framework for implementation. Abstract versions of it are used to express abstract algorithms. Um, More language-specific versions of it are used to express design for programs in those languages. Pseudocodes supposed to be clear enough that a human being can execute it by hand without using a computer and with a little or no knowledge of programming languages. Pseudocode is used to represent the algorithm. The common characteristics of pseudocode statements are written in simple English. Each instruction is written on a separate line. Let's check our example here. Let's check our example. Statements are written in simple English. Here's our statement. Our statement says if else. If else, there is a statement. If d is greater or equal to 0, then then x1 is equal to our instruction. These are our instructions. So if d is if d if d is greater or equal to 0, then x1 is equals to minus b or plus. Those are instructions. So basically, from our slide, statements are written in a simple English. Each instruction is written on a separate line. Instructions on a separate line. But if else, this is on line 6. This is our first instruction. On line 11, this is our another instruction. Else if d is equals to 0, then, and then else, this is our another instruction. So uh, our instructions are written on separate lines, which is true. We have seen that. So now keywords and indentations are used to signify particular control structures. Each set of instruction is written from top to bottom with only one entry and one exit. Groups of statements may be formed into modules, and the module given a name pseudocode is like an English-like non-standard language that lets you state your solution with more precise than you can in plain English, but with less precision than it is required when using a formal programming language. Pseudocode permits you to focus on the program logic without having to be concerned just yet about the precise syntax of a particular programming language. However, pseudocode is not executable on the computer. Documenting the program. Documenting is an ongoing necessary process. Although as many programmers are, you may be eager to pursue more exciting computer-centered activities. Documentation is a written detailed description of the programming cycle and specific facts about the program. Typical program documentation materials include origin and nature of the problem, a brief narrative description of the program, logic tools such as flowcharts and pseudocode, data record descriptions, program listings, and testing results. Comments in the program itself are also considered an essential part of the documentation. Many programmers or compilers document many programmers or compilers document as they code. In a broader sense, program documentation can be part of the documenting for an entire system. The wise programmer continues to document the program throughout its design, development, and testing. Documentation is needed to supplement human memory and to help organize program planning. Also, documentation is critical to communicate with others who have an interest in the program, especially other programmers who may be part of a programming team. And since turnover is high in the computer industry, written documentation is needed so that those who come after you can make any necessary modification in the program or track down any errors that you have missed. So now, guys, we are done with our first session of 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 the day. We just wanna let me just recap of what we had been the session was all about. We tackled we tackled almost everything. The rest for you is to read and understand what is all that about. Our it will be, yes, our first session for today. What we have tackled so far, our recap. We have mentioned the problem analysis, having to explain the problem analysis. What is the problem analysis? Which is a process where we have to break down problems so that those problems can be easily be meaningful to us, which is we need to understand. And then after analysis of the program, you need to put down the steps that must be followed for the solution. And then these steps are written for the computer in order for you to produce the desired result. And then those steps are your algorithm, are known as an algorithm. And an algorithm is an instruction designed in such a way that if instructions are executed, the sequence, the desired result will be obtained. So now, from our learner guide, these our this is our 7 steps processes of the program development, 7 step processes. So first things first, there are 7. We need to understand the problem, and we need to plan the logic of the program. Understand the problem. Understand the problem. You need to understand what is the problem. It's under analysis, problem analysis, problem analysis, problem analysis. So now we need to analyze the problem first. Analyze it. Analyze it. Put it in a much more easier way for you to understand it. Make that problem be meaningful to you. Understand that problem. Understand. Then plan the logic around the program. Now you need to plan the logic around the program and encode the program using a structured high level computer language code. You may use for those compilers or programmers that wants to use Ruby, for example. Yeah, fine to use Ruby, for example. It's fine for you to use Python. It's still fine for you to use Java. It's still fine. It's either way, whether you want to use Visual Basic, and it's still fine to have a compiler know 2 or 3 high level high level computer languages, and then using a compiler, a programmer, translate the program into a machine language, test and debug the program, put the program into production, and then maintain and enhance the program. So you have to maintain. The most important thing with the program is that when an application is being developed, so each and every time after a certain time, like for instance your operating system, it's a high level machine language, an operating system. So now each and every time an operating system, your Windows, there are a couple of operating systems. Well, there's Windows, there's Macintosh, Mac, there's Ubuntu, there's a Linux, and there's a Unix. So I'll just mention that that we are familiarized with, which is the Windows. So the Windows operating system, each and every after some time, they release the fixes within the Windows. So those fixes is when they maintain and enhance the program to say we have spotted a vulnerability within the program. So this is the fix to fix that program. So that is in a part of the 7, which is maintaining and enhance the program. So they maintain the program each and every time. The compilers have to maintain the program. They need to see whether the program has vulnerability within itself. So those are the things when they mean maintain, and put the program into production. We need to take those OSs, install it into our PCs, and then we test whether that program and the users can interact with the program itself. Let's just go down the flowchart. We've mentioned that a flowchart is just a graphical representation using a set of geometric symbols. It could be a plus plus, it could be a plus plus. Well, that example, this, perfect. So where we see your equals to, like the statement if D is greater or equal to. That is our flowchart. It uses a set of geometric symbols. That is our flowchart. So the statement here, the statement which is an algorithm, a sequence to say if D is greater than or equal, those greater than or equals to are our flowchart. Those are our flowchart. So it explains further. So now those are the graphical. Those are our graphical representation of steps controlled used in an algorithm. So those control lines to describe the algorithm. So a programmer can produce a high-level code required to compile an executable program. So those are our flowchart. So where you see your greater than or equal to, those are our flowchart. So let's just recap of what we were doing. Mm, the three types of three types of control structures, which is our sequence, decision, and iterative. Looping, which is all looping. We know that the three types of sequential structures is the process, input and output, and subroutine call. And the three types of decision structures, which is the single branch, double branch, and a case. Four types of iterative structures: test at the top, test at the bottom, counting, and end user control. And the problem analysis technique, which is at least two. It's the top down and the bottom up. You need to understand what's the difference between that, and then you need to know um, and the product design and development that uh, during the design of new products, engineers and designers, they rely on these two approaches, which is the bottom up and the top down. So you need to know that. Just read through. And the modularity, which is named modules. And what is the modularity? Designing a system that is divided into the set of functional units, so that can be composed into a larger application, and it represents a set of related concerns, and it can include a collection of related components such as features, views, or business logic. So basically you need to go through that as well, read, study, just know these kind of things, so that you could able to answer your activity, because there will be an activity uploaded which will require you to engage and to answer. So you'll be tracking you'll be tracking your engagement in terms of participation. You'll be tracking your participation within the e-portal. So you need to understand why would you want to choose a modular design. Why you want to choose. So these are the following scenarios, describing and explaining further, for you to understand why would you want to choose a modular design. So a pseudocode, I've explained it in terms of saying a pseudocode. It's a it's a it's a it's a it's a high level description of a computer program or algorithm. You need to bear in mind that an algorithm what it is, set of sequence structures, set of it's an instruction. An algorithm is an instruction. You reach a stop sign will tell you when will tell you the sign that says a car has to stop. So that is an algorithm. So when you see a robot, when the robot is red, an instruction tells you that you need to stop. When it's green, an instruction tells you that you need to the car has to go. When it's orange, you need to stop down. So those are instructions. They are sequence instructions of an algorithm. So a pseudocode is a high-level description of a computer program or an algorithm. So just doing a recap of what we were doing today, you need to read through and understand the flowcharts are both popular ways of representing algorithms. You remember flowchart is it's your graphical representation of geometric symbols. Your plus plus, your equals to, your greater than, or your less than. Those are graphical representations of geometric symbols. So you have to go through that and read through, and you're encouraged to do research in terms of doing extra research and understanding better. So that will help you to understand better and have a different perspective in terms of what is all about this, and you'll be ready for your activity. So guys, uh, today our first lesson, we are done with our first lesson. So we will send our next video, which is on the activity. We'll go through the activity together and in our next video. So guys, thank you for tuning in, and I hope you guys are ready for our next video, which is we'll be going through our activity. Thank you very much guys, and we'll see each other in due course.